Okay, so it is my great pleasure to introduce Lisa Piccirillo from University of Texas at Austin, who is the plenary speaker of the second part of today's conference, and she's going to talk about new constructions and invariants of closed smooth form manifolds. So Lisa, it is to you now.
Thanks. Yeah, thank you so much to the organizers for inviting me. I was a little bit surprised to be invited because I think about form manifolds far more than I ever think about knots. So hopefully you'll kind of bear with me today. This is a talk about form manifolds. And let me maybe start off by just setting some conventions. All the manifolds that I talk about today, I'm going to be assuming are smooth. I'll also be taking them to be compact oriented, and unless I explicitly say otherwise, they won't have any boundary. Okay, so I'm interested in trying to understand form manifolds. And we know a lot less than we'd like to, but maybe if there's one theorem that you've heard and you know about smooth form manifolds, it's Friedman's. My slides aren't advancing. Let's see. There we go. Great. Who gives us a classification up to homeomorphism of simply connected smooth form manifolds. So he's going to tell us that they're determined by their intersection form. Good. So this is a fantastic theorem. It's to this day like probably the strongest thing we know in a positive direction about understanding smooth simply connected form manifolds. But it's a little bit unsatisfying. You know, I want to study smooth form manifolds up to diffeomorphism, not up to homeomorphism. So okay, you want to know if this theorem, like if smooth form manifolds are determined up to diffeomorphism by their intersection form, and you know if there's maybe a second theorem that you've heard before about smooth form manifolds, it's that they're not. Donaldson shows us that there are simply connected form manifolds where the diffeomorphism type is not determined by the homeomorphism type. And for example, he shows that there is a smooth form manifold that is homeomorphic but not diffeomorphic to CP2 connected some 9 CP2 bars. And it's this kind of pair of results, and in particular Donaldson's result, that kind of kicked off what I really want to talk about today, which is the study of exotic form manifolds. So let me define exotic to mean that, or I'm going to say that a form manifold is exotic if there is some other form manifold which is homeomorphic but not diffeomorphic to it. Checking in quick, can people see my cursor?
Yes, yes, yes.
Excellent, great. Good. So Donaldson shows us that there are exotic manifolds. Fine. So it's not, you can't determine a smooth manifold just by determining its homeomorphism type. And so that leads us to, you know, well, we'd like to understand smooth form manifolds. So kind of you have to come back to the question, like how should you try to understand a diffeomorphism type of a smooth form manifold? And that's probably, you know, what should be the main goal of the field. But there's an issue, which is that this question is like super hard. We don't have any results about this. We don't have any conjectures or tools that we could use to prove a conjecture if we had one. We're sort of very far away from being able to actually give a classification type result for simply connected smooth manifolds up to diffeomorphism. Okay, so that's kind of bad. And what that has done to kind of the literature and the way people have been thinking about simply connected smooth form manifolds for a while now since Donaldson's results is that if we really just have no idea how to approach this question, maybe we should ask a slightly easier question to try to build some tools. And the slightly easier question is sort of, okay, Donaldson shows us that there are simply connected form manifolds that aren't determined by their homeomorphism type, but is that always going to be the case? So in the language of exotica, the sort of new goal is every simply connected manifold exotic? And another thing that kind of motivates this secondary goal is that it includes within it, I suppose, the Poincare conjecture, which in this language posits that the force sphere is not exotic. And this kind of secondary goal has produced quite a lot of literature. We'd be here for a long, long time if I tried to sort of survey it properly. So let me just tell you kind of the shape of how the literature has gone and the sort of most current result. The sort of strategy is that one way you might try to approach the Poincare conjecture, asking whether this like very, very simple form manifold is exotic, is you might try to produce simply connected exotic manifolds with smaller and smaller B2. So Donaldson's examples have B2 equals 10. And then there's a progression of literature after that, getting this smaller and smaller. The state of the art is a 2008 result from Akhmedov and Park, where they get B2 to B3. And more or less since 2008, so going on 20 years, and we haven't had any further improvement in small, simply connected exotica, which to me motivates maybe a third goal question, and that is the question that motivated kind of the work I want to tell you about today, which is if the techniques that were used previously to prove this have kind of stalled out, then maybe we're interested in developing some new techniques for this question. So that's kind of the motivation for the project I want to talk about. Let me check in for questions. Maybe also let me say, I mean, I know Zoom is like terrible for the soul, and for some of you it's cold out and whatnot, but I like really like to get a lot of questions. I'm gonna pause and ask for them like a lot. I'm gonna wait around and see if any percolate. So like please, I also have an eye on the chat. So anyway, please don't hesitate to ask me questions. All right, well, maybe next time. Okay, so new techniques for producing small-ish simply connected exotic manifolds is what motivated this work that I did with Ty and Adam that I want to tell you about today. So just a comment how the slides are going to work. That last slide has moved over here to the left. We'll get new stuff over here and we'll keep progressing. Okay, great. And so the project I want to talk to you about is, right, to give new techniques for producing exotic manifolds. But that's not like a theorem on its own. So let me give you a couple like oh Lord. There's an issue sometimes where I move the mouse and we jump like 10 slides. Okay, here's a couple of statements that we can prove with our techniques. So for one, we can show that CP2 blown up 9 times is exotic. That maybe looks familiar. That's what Donaldson proved a long time ago. So fine, not a thrilling result, but we give a pretty different argument, both constructively and obstructively. An argument is and our construction is a little bit more hands-on. And so kind of as a part of how we built it, we were able to build it with a free involution. So we could look at the quotient manifold and produce exotic manifolds that aren't simply connected, that have a little bit of pi 1. But at the expense of a little bit of pi 1, B2 is fairly small, not quite as good as Akhmedov and Park, but fairly small. And in fact, these manifolds have definite intersection form. And this was the first example of definite exotic manifolds. And this was a little bit surprising because there's some other kind of aspects of form manifold topology where definite and indefinite form manifolds behave pretty differently. So it was like somewhat reasonable to conjecture maybe that exotica only was a phenomenon that happened for indefinite manifolds. So we show that's not true. Following our work, there's been like some really excellent, really just sort of better work that combined our techniques with some more classical approaches. So the first kind of follow-up theorem I wanted to tell you about is work of Stipchus and Szabo, who showed that in fact there are exotic manifolds with pi 1 z mod 2 where B2 is 1. So really quite small. And again, the intersection form kind of has to be definite. And I think that, okay, it's not simply connected, but I really think that you can think that this is, in some senses, the first progress we've had on like very small exotic manifolds in a long, long time. And following that, there's another really fantastic result, also not of me. This is from Baker, Stipchus, and Szabo, who in fact prove a much more sweeping statement. So they're going to say that for pi 1 z mod 2, an odd intersection form, essentially all smooth manifolds are not determined by their homeomorphism type. So they're really kind of coming back and addressing this goal question for most odd z mod 2 form manifolds. So the plan for the talk is to tell you a little bit about the techniques that we developed to prove the 2 results I have here. I'm sort of more interested in talking about the techniques because I think exotica is something that has a scary name and some of the old proofs are pretty gnarly and maybe a lot of people are a bit turned off by. So what I really want to highlight today is that our techniques are fairly straightforward and hands-on. So I'm not going to prove either of these results. I'm going to prove a result that probably looks to you worse. So it goes, come on, there we go, which is this one. That they're exotic manifolds with pi1z and with b2 equals 14. So this is much more homology than we had before, much more pi1, but the proof of this is really kind of straightforward, and I think it illustrates our method. So that's what I'll talk through. Any questions here? Okay, well, fine. So to start telling you what the techniques are and how you prove an exotica theorem, at least the way we like to think about it recently, let me just give a quick outline of how you prove an exotica theorem ever. And I usually think of this as a three-step process. So the first thing you need to do if you're going to try to produce exotic manifolds is build a pair of candidates. So smooth manifolds, which you have some reason to think might be homeomorphic and not diffeomorphic. Then you need to show they're homeomorphic. Then you need to show they're not diffeomorphic. So this is not a very sophisticated outline, but I want to talk through kind of the methods for each step as we go. And I want to start with the kind of the second step, the homeomorphism, because that's what we don't really have anything particularly new to say about. So I told you sort of on the first slide that for simply connected manifolds, we understand pretty well how to show that they're homeomorphic. Friedman tells us that their homeomorphism type is just determined by their intersection form. So if you have your candidates, then you can just compute their intersection form. And if they match, then they're homeomorphic and you get to move on to step 3. But we're going to prove a theorem about pi1z manifolds. So this is not quite going to work to produce homeomorphism for us. But fortunately, there's a theorem for pi1z manifolds. So to set that up, let me remind you, I think most people know, but just for people who don't think about form manifolds too often, the intersection form is this bilinear pairing. I like to think of it on H lower 2 as this pairing that counts the intersection between surfaces representing those homology classes. But if you like, you can think of this as the cut product pairing on H upper 2. So this is this intersection form that Friedman's talking about here. And that's going to determine the homeomorphism type of a simply connected manifold. For a manifold with pi1z, we want a little more. We want something called the equivariant intersection form, which is essentially the same thing, except instead of looking at H2 of the manifold, you're going to look at H2 of the, if it's a pi1z manifold, of the infinite cyclic cover. And instead of just getting kind of an integer for your intersection count, you're going to get a Laurent polynomial where you're thinking of that variable as loosely counting kind of how many deck transformations do you have to do before the intersection happens. So this is like a variation of the intersection form that just records also how those intersections interact with the pi1 of the manifold.
Do you use any action of the fundamental group? Where do you take T? Fundamental group or what? Where do you take T?
It's a deck transformation up in the cover. So I'm really kind of saying, I'm thinking about this as H2 with coefficients in Z TT inverse. And so I'm intersecting kind of a surface with all of its translates, and I'm counting which translate with the T. Good. And so the theorem, and this is now Friedman and Quinn from the 90s, is that this equivariant intersection form is going to tell you the homeomorphism classification of smooth pi1z manifolds. Good. So that'll mean that for Ty and Adam and I, the work we're going to actually have to do is just steps 1 and 3, build candidates, and then we'll just get the equivariant intersection form right. That'll make them homeomorphic, and then we'll have to show they're not diffeomorphic. More questions here? Okay, great. So I'm going to start out then with talking about 3. Once we build candidates, how are we going to tell them apart? And the kind of structure we're going to use comes from Hager-Floer homology, which is this invariant package, Duda, Schwarz, and Szabo from the early 2000s. And I think a lot of people here looking at the participant list are not Hager-Floer homologists. This is going to be like the gentlest overview of Hager-Floer homology you've ever seen. I suspect you've heard people say that before, and it wasn't that gentle, but this one's actually going to be gentle. So here's what I need you to know about Hager-Floer. It's an invariant package that's going to take a 3-manifold and assign to it a module. So, okay, that's an invariant for 3 manifolds. It also comes with an invariant for certain 4 manifolds. In the following way, whenever you have a cobordism between 2 3 manifolds, that's going to give you a map between the modules for those 2 3 manifolds. So this is a 4-manifold invariant. A map is a perfectly good invariant. However, it's just an invariant of a certain type of 4-manifold, in particular, one with boundary. So kind of out of the box, this isn't an invariant of closed 4 manifolds. There's kind of a natural way to try to cheat. You could say like, all right, I'll take my closed 4-manifold, I'll puncture it twice. Now it's a cobordism from S3 to S3. That'll give me a map. But the modules for S3 are going to be trivial. So there's just like not enough. There's not going to be any information if you kind of try to sneak out a closed 4-manifold invariant in that way. Okay, so there is a way in the kind of classical Hager-Floer theory that Schwarz and Szabo tell you can get an invariant for closed 4-manifolds by doing kind of a whole bunch more work here. But Adam and Ty and I define kind of a new way of extracting a closed 4-manifold invariant just from kind of these 2 basic things that the Hager-Floer package gives you. And our invariant is set up in the following way. So we're going to call this thing the alpha invariant. And let me just define it today for 4 manifolds with B1, so the rank of the first homology to be 1. And how we'll define the invariant is we'll say, look at all the 3 manifolds that embed in the 4-manifold and generate H3, and ask sort of what's the smallest Hager-Floer homology of any of those 3 manifolds. This is, kind of like an analog of the Thurston norm, where you're saying what's the smallest surface that represents some H2 class. We're saying, in a sense, what's the smallest, the Hager-Floer smallest 3-manifold that generates my H3 class. And maybe a first kind of observation about this alpha invariant is that if you look at a 3-manifold that you get by taking S1 cross S3, so that's going to have a little bit of B1 and B3 here, and just connect summing it with anything simply connected, well, any manifold like that is going to have alpha invariant 0, because you have this S3 that generates H3. And, well, fact, that your homology, if that's trivial. Oh, boy. I don't quite know why this happens sometimes. That means I'm not going to have any surprises in my talk. Sorry. Where are we? Here. Great. Okay. Any questions here, just about the definition of the invariant? Okay, so, fine, that's an invariant. You can define it, and you don't have to prove it's an invariant because we defined it by taking a minimum. But you should think that I've, made a deal with the devil here. The downside of defining an invariant by taking a minimum is that generally speaking, you can't compute it other than, when it's 0.
Well, the most known work of yours is with the Conway knot, where you used Rasmussen. So you used combinatorial techniques, and here you use Hager-Floer. The most natural question: can you use Khovanov, or can you use any combinatorics without this all techniques of homomorphic structures or whatever else we share? Sit inside this package.
Yeah, so we don't know how to prove an analog of like the manifolds in a build from Kavanagh homology right now. That's something people are working on pretty actively, is setting up. Right now, Kavanagh homology isn't really defined in other 3 manifolds, just defined for knots in S3. People are working on that. There's a skein lasagna stuff. There is an exotica result from our 4 manifolds with boundary from skein lasagnas now. But I don't know how to run like the techniques that I'm talking about here in the Kavanagh setting. More questions? Okay. All right, so we have this invariant. It's invariant for free because we took a minimum, but you're worried that I can never compute it, which is a pretty valid thing to be worried about. But let me try to tell you that I can compute it sometimes. So here's a lemma. It's going to be of the following structure. If something happens, then I'll be able to say the alpha invariant of my manifold is something. So to fill in the blanks, I need a little bit of setup, but this is the kind of lemma I'm going for. Okay, so what's the setup? Here's my manifold X. Remember, we're studying manifolds that have a little bit of B1, so I've drawn this with, kind of a circle direction representing that. And now take X and choose some 3-manifold Y sitting in there generating H3. Now what you can do is you can cut X open along Y. That'll look maybe something like this. And what does that give you? It gives you a cobordism. And in fact, a cobordism from Y to itself. So then the Hagar-Floer package is going to give me an automorphism of the Hagar-Floer of Y then from this cobordism. And the lemma says that if that automorphism is in fact an isomorphism, then Y is minimizing. So I can actually read off the alpha invariant of this. It's just going to be the rank of Hagar-Floer of this. And I'm going to outline a proof of this. It's sort of not too bad. Any interjections before I do? Okay. So how does the proof go? We're going to look at the infinite cyclic cover of X, which maybe you're picturing looking something like this. It's like a stack of a bunch of these cobordisms. Okay, now let's suppose that I had some other 3-manifold Y prime that also generated H3. I can take a lift of it to the infinite cyclic cover. Maybe this should have a tilde on it, sorry. But you have some lift up here. And by compactness, I can be sure that there is some kind of finite set of fundamental domains where this lift of Y prime is contained there. So I can find some big cobordism W from Y to itself that Y prime sits inside. Okay. Now I want to take that cobordism W and kind of factor it into 2 smaller cobordisms, W1 from Y to Y prime and W2 from Y prime to this other Y over here. And okay, something I didn't tell you, but is what you would want and is true. These Hagar-Floer cobordism maps, they do what you would want under composition, meaning if you stack cobordisms, you're going to get a composition of maps. So the map I'm going to get from this big cobordism W is going to be a composition of these 2 smaller cobordism maps. Oh. Okay, there we go, great. Okay, but this big cobordism map, what is that? That's just a stack of these X minus Ys. So that's going to be inducing an isomorphism on the Hagar-Floer of Y. But it's also going to have to factor through the Hagar-Floer of this Y prime cut here. And so since the big map's an isomorphism, the rank of the cut can't be any smaller than some rank on the edges. Any questions here? So coming back to our sort of how do you produce exotica outline, this is the invariant we're going to use to do step 3. And maybe what we'll want to have in mind as we come back and actually try to build a pair of manifolds that will hopefully be homeomorphic and diffeomorphic and not diffeomorphic is that, well, if my computational lemma says that I have to be able to cut my thing open and have an isomorphism on Heger-Fleur, that's maybe something I'm going to want to try to build into my setup here. Okay, so how do we build our candidates? Let me start by telling you what the kind of elementary building block is going to be that we'll use to build X, and it's something called a two-handle cobordism, which maybe people here have seen a bit before, but I want to set up in case we haven't. So what's a two-handle cobordism? It's a cobordism that you build in the following way. You start with some three manifold, anything you want. You cross it with I, just kind of for formal reasons to get started. And then morally, a two-handle cobordism is just going to be the manifold you want to get by gluing a two-dimensional disk onto one side of this. So how does that kind of work? Well, you know, the boundary of a two-dimensional disk is an S1. So if I want to glue that onto like this copy of Y, then really I'm just specifying some not in Y. I really don't understand when I touch my mouse, like when that makes it do something to the slides. Sometimes it does, sometimes it doesn't. The algorithm is very unclear to me. But okay, two-handle cobordism is basically a D2 glued onto Y cross I, and you're just going to pick like what knot do you want to glue the boundary of the disk to. Okay, but of course it can't actually be that because that's not a four manifold. So to make it a four manifold, you want to think that this disk has actually been thickened up in another 2 dimensions. So this whole thing is kind of globally 4-dimensional. But morally, like the important bit of the topology of this two-handle cobordism is that there's a disk there that you've stuck to some knot. And kind of schematically, you know, what's this look like? It's this cobordism, starts with whatever 3 manifold you picked Y, and then the kind of boundary over here, like, well, you've modified it a little bit when you stuck this stuff on to the neighborhood of your knot. In fact, the modification will be a Dane surgery. We don't really need to know that today. But what this is really going to give you is just this fairly simple cobordism from Y to some Y prime. So these are how I'm going to build my exotic manifolds. And we'll circle back in a second to actually sort of building a whole exotic thing out of these two-handle cobordisms. But let me check in for a minute about this question you should be maybe worrying about, which is, can I compute the Heger-Fleur maps that these cobordisms are going to induce from the Heger-Fleur of this 3 manifold to this new one? Maybe something some of you know is that Heger-Fleur is not algorithmically computable, at least not in many of the theories. So this is kind of a real pressing question. But the answer is, you know, maybe sometimes. So let me give you a setting where I can compute these two-handle cobordism maps. And this is, again, going to come from a theorem of Oshwath and Szabo, who tell me that there's an exact triangle that contains the map that I care about. So the triangle has, for one side, this two-handle cobordism map going from the Heger-Fleur of this manifold to this one. And then, well, you know, it has something else. There's this other term, which is a Heger-Fleur of some explicit third auxiliary 3 manifold. So this is a theorem, is the exactness of this. And why am I telling you about it now? Well, because there's a obtuse but practical thing you can try to do, which is if you want this map to be, let's say, an isomorphism, you can force that to happen by attaching your two-handle in a way where this auxiliary 3 manifold has trivial Heger-Fleur homology. That forces an isomorphism across the top. So that's kind of crude, but it turns out to be enough. So if you want to build your manifolds out of two-handle cobordisms, you can expect to get isomorphisms as long as you're prepared to be careful about how you do your attaching so that this manifold is pretty simple. Questions here? Okay, so with that, we are kind of prepared to prove the results I wanted to talk through. So on the left is a bit of a modification. I'm kind of collecting what we're going to need. So here's that exact triangle we just had. Here's the computational lemma from before that says what I need to be able to sometimes pin down the alpha invariant, and here's the result I'm trying to prove. So exotic 4 manifolds with pi1z and with B2 equals whatever I can make it be, which will turn out to be 14. So here's how it goes. I'm going to start by building one of the manifolds that'll be, in my exotic pair. So to build that, I'm going to start. No. Great. I'm going to start by building a cobordism. And I'll build it in the only way I just told you how to build cobordisms. So I'll start with some 3 manifold, cross it with I, and then I'll attach a stack of these kind of 2-handle cobordisms. That'll be some global cobordism W. And I'm going to do this forcing a few extra things to happen. So here are the conditions I want W to satisfy. For starters, I'm going to choose a starting manifold where the rank of Hager-Floer is strictly greater than 0. And secondly, I'm only going to attach 2 handles so that this exact triangle tells me the 2-handle cobordism map is an isomorphism. And these 2 conditions together, the reason I'm going to want them is to hopefully be able to apply the lemma to get some non-vanishing invariant eventually. Okay, so certainly I'm going to need those 2 things in this cobordism. I also want to force the fundamental group of this cobordism to be trivial. I claim that's a sort of reasonable, it's reasonable that you should expect I can do that. So I'm starting with some 3 manifold cross I, so that's going to have fundamental group for sure, probably something kind of sophisticated. But what's a 2-handle cobordism? It's basically a disk. So every time I attach a 2-handle, I'm going to get a relator on pi1. So you should kind of believe that if I'm careful, I can kind of knock out the 3 manifold group and get a pi1 of the cobordism trivial. Okay, so I'm going to make that happen. And then the final thing I want to make happen is I'm attaching all these 2-handle cobordisms. We kind of said every time you attach a 2-handle, you change the boundary by a Dane surgery. And the final thing I'm insisting is that sort of Dane surgery sequence is a loop. So I'm going to arrive back at the same 3 manifold I started with. And this is kind of the tricky bit if you want to go home and do this again for yourself. Okay, but if you can do all of that, then you're in business. You're ready to prove the theorem. Here's how it goes. So we're going to define X to be this cobordism with the ends glued together. That's what I needed this last bullet point to be able to do. The lemma is going to tell me, this lemma here, that the alpha invariant of X now has to be non-zero because the alpha invariant of this cut is non-zero, and this is an isomorphism. This cobordism induces an isomorphism on Hager-Floer of Y. Okay, because this cobordism was simply connected, when I glue the ends together, I'm just going to get something with pi1z. So that's good. That's what I want. So this is going to be one of my 2 manifolds. The other manifold, I'm just going to kind of get out of the museum of well-known manifolds. It'll be S1 cross S3, connect some 2 copies of CP2 and 12 copies of CP2 bar. Okay, so where did that come from? Why did I fish that out of the manifold museum? Well, I fished it out exactly because I computed the equivariant intersection form of the X of the manifold I built, and it was the same as the equivariant intersection form of this guy. So that's going to be who I want to compare the thing I built to. So they have the same equivariant intersection form, so Friedman can tell me the thing I built is homeomorphic to this guy. But as we commented in the beginning, this guy, this X prime, has to have alpha invariant 0 because it has this S3 generating H3, just by definition. So these things don't have the same alpha invariant, so they're not diffeomorphic. Any questions here? Okay, well, in fact, oh, is there a question? No.
Yeah, yes, actually. I'm trying to, I mean, maybe this is a deeper question, but F2 handle being an isomorphism. What does that really mean? I mean, what topologically, can you say something even vague? It just seems like there's a lot captured in that statement, right? Like,
Yeah, it's hard to give you anything topological. I mean, I can give you like there's other ways to sometimes prove that some induced map is an isomorphism. I mean, I guess what it's just saying is there's not this huge information loss, or the cobordism gives a sufficiently tight relationship between the two 3 manifolds that it's going to manifest in a tight relationship between their invariants.
okay, so this exact triangle by Ajvat and Szabo, is that sort of an explicit construction? Is that what you said, that it's quite explicit? So if I sort of really looked at that, maybe I would understand a little more about
Yeah,
constructively what this means.
yeah,
Okay, thanks.
of course. Okay, we have one in the chat. Have there been other similar invariants to alpha invariant from Hager-Floer that have been used to prove further results? Or do the other results also use the alpha invariant? Right, so the other, if you're referring to like the Stipchit-Szabo and the Baker-Stipchit-Szabo results that I mentioned in the very beginning, those were not proven using the alpha invariant. Those were where they kind of do the work is for simply connected manifolds, so alpha invariant doesn't quite make sense there. They're going to use something called the mixed invariant, which is kind of the standard way to cook up a closed 4-manifold invariant from the Hager-Floer package. To my knowledge, there haven't been any further applications of the alpha invariant since our work. More questions? Okay. Well, in fact, that's what I wanted to say. So thanks again so much for coming.
Okay. Thank you so much for this exciting talk and very instructive. Are there questions, comments? There is time for discussion. Lisa?
Okay, we got one in the chat. Do you think it's possible that your methods with some smart choices could show the existence of an exotic S4, assuming one exists? No, I think they absolutely can't. Here's a couple of reasons. One, this alpha invariant thing, we really only know how to define it in the presence of B1. But then there's kind of an even bigger problem, which is like any invariant that comes from Hager-Floer homology or gauge theory more broadly has to vanish on anything homotopy equivalent to S4. So nope. But thanks for the question.
Hi, Lisa. Thanks for the talk. I had a question just regarding the so these two-handle cobordisms. How easy or difficult is it to perhaps draw like explicit Kirby diagrams or like handle diagrams of the cobordism?
Oh, completely easy and explicit. We give a handle diagram, like a complete handle diagram of this cobordism W, for example.
Okay. Thanks.
Yeah, of course.
More comments or questions? Okay.
I have a question. Is this producing infinitely many examples because you've got lots of choices for the initial Y?
Yes. For example, yeah. So we give